last section we talked about average rate of change. Now we're going to look at what we're going to consider instantaneous rate of change. So if you remember, average rate of change was the ratio between two function values over two x values. And we calculated that out. It gave us a number that showed us the slope of a secant line between 2 points. Okay. The instantaneous rate of change is the rate that a function is changing at a particular point. So no longer over an interval, but at an instant point. Okay. And we denote it this way. IRC is the limit as x approaches x naught of f of x naught minus f of x over x naught minus x. Okay. So if we look at our graphical representation, it says that if I've got 2 points, so x naught and x, and I am going to move my x in this direction, then I'm basically looking at all of the secant lines between my point and x naught. Okay? The limit, what this is doing is it's saying as I move closer and closer, so if my x moves a little closer in, notice my secant line is going to change. Okay? And eventually this limit, as these points get really close together, so if my x and my x naught are pretty much the same point, what happens is my secant line turns into what we call a tangent line. And so our instantaneous rate of change the IRC basically tells us the slope of the tangent line of a curve. And in later sections we'll talk about why we want to use this in terms of mathematics and why this is useful for applications. For now, let's look at how to actually find this instantaneous rate of change. Okay? So we're looking for the slopes of the tangent lines. Again, just like with the average rate of change, you're going to start by finding some for specific values. Okay? So let's look at this first example. G of x equaling 4x minus 3. We want to find the instantaneous rate of change when x naught is 2. Okay? So again, if we think of our formula here, it says my instantaneous rate of change is going to be the limit as x approaches 2, f of 2 minus f of x all over 2 minus x. Okay? And again, for these, that first part, the f of 2 and the f of x, just means I need to plug in what the functions are there. And I'm going to apologize, these should be g's. Okay, so if we look at g of 2, we can plug into our function there. This is going to be the limit as x approaches 2 of 8 minus 3, which is 5. G of x is 4x minus 3, all over 2 minus x. Okay. Here we can simplify some things. So notice 5 minus a negative 3 is just 8. So this is the limit as x goes to 2 of 8 minus 4x all over 2 minus x. Okay. Now at first look, this is fairly difficult to find the limit. But if you take a slightly closer look at it, you'll notice that the numerator can be factored. Notice here I can pull a 4 out of the top, and I'll get a 2 minus x over 2 minus x. We can cancel the like factors. So we're looking at the limit as x goes to 2 of the constant 4, which is just 4. Okay. So this tells us our instantaneous rate of change, or again, the slope of the tangent line at that particular point is just 4. Okay. Now again, just like with our average rates of change, we said if we're looking at a linear function, the average rate of change should be the same as the slope. Well, the same thing should be true for a linear equation and the instantaneous rate of change. My slope of my tangent line should be the slope of the equation. And here we can see that. In the linear equation 4x minus 3, my slope is 4, and my instantaneous rate of change is 4. Okay. Let's look at another example. Let's look at f of x equaling 5 over x, and the point we want to find the instantaneous rate of change is going to be 6. Okay. So here our instantaneous rate of change is going to be the limit as x approaches 6 of f of 6 minus f of x all over 6 minus x. Okay. Again, just like before, we need to plug in and find the top portion. So limit as x goes to 6 of 5 over 6 minus 5 over x all over 6 minus x. Now again, at first look, it looks very difficult to solve, but again, we're going to have to use some algebra to rewrite and simplify this expression. So again, notice you've got a complex fraction. So again, we'll get rid of that extra denominator. So cross multiplying says 5x minus 30 over 6x times 6 minus x. Okay. Again, just like in the last case, we see that the numerator can be factored. So again, we can pull a 5 out of there. More importantly, I can pull a negative 5 out. And again, we can see some things will cancel. So here, our limit as x goes to 6 is going to be of negative 5 over 6x. Here, as we take our limit, we can see this is going to turn out to be negative 5 over 36. Okay, so there's our instantaneous rate of change, which again just tells us the slope of our tangent line for that particular curve at x equals 6. Okay. Let's look at one more concrete example. Let's see h of x equaling the square root of x minus 3 at x not equaling 12. Okay, so this one we're going to do kind of the same way. Our instantaneous rate of change, limit as x goes to 12, of our h of 12 minus h of x all over 12 minus x. Okay. Here again, we'll start by putting in the values. So limit as x goes to 12, h of 12 looks like the square root of 12 minus 3, which is just 9. We can simplify that down, minus the square root of x minus 3 all over 12 minus x. Okay. Again, notice square root of 9 is just 3. So again, we want to take the limit at this point. Now, notice on this one, there's not a nice way to just rewrite and factor out. But again, remember, anytime I have square roots, there's always the use of the conjugate to rewrite things. So here, if we multiply top and bottom by that conjugate, so 3 minus square root x minus 3, we'll multiply that by 3 plus square root x minus 3. Do the same thing on the bottom. Okay. On the top, we can see that we'll multiply out. multiply out, we'll get a 9 and the 3 times 3. Notice the middle terms, when we FOIL this, will cancel out. And we're left with a minus an x minus 3 over the entire denominator. Okay. Now, if you look closer at the top, when I simplify there, distributing that minus sign, we see that we get a 12 minus x, which is exactly the same as the factor in the denominator. So we'll be able to cancel those out. And we're left with the limit as x goes to 12 of 1 over 3 plus the square root of 12, x minus 3. So we're left with the limit as x goes to 12 of 1 over 3 plus x minus 3. Okay. Now taking the limit, because we can now plug in, again we'll see 12 minus 3 there gives us a 9, square root of 9 is 3. So we're looking at a 1 plus 3 over 3, 1 over 3 plus 3, which is 1/6. There's our instantaneous rate of change for that particular function at x equals 12. Okay. Our last example is one that is more arbitrary. So again, just like with our average rates of change, we can look at arbitrary intervals and find a function that will give us the average rate of change over that arbitrary interval. For the instantaneous rate of change, we can do the same thing. So given a function, I went back to a nice polynomial, but it could happen with any of these types of functions we've looked at. Given a polynomial function, we want to find the instantaneous rate at this particular value, so at x plus h. So again, instead of looking at some pinpoint value that we know, we're looking at kind of a generic one. We're going to end up with a formula for our average rate of change for any value of x. Okay. So our instantaneous rate, again, says limit as x goes to x plus h, f of x plus h minus f of x all over x plus h minus x. Okay. Plugging in, so as x goes to this x plus h, f of x plus h looks like x plus h squared minus 3 times x plus h plus 1 minus our f of x. Again, don't forget to distribute your minus sign here. All over h. Simplifying, we'll multiply some things out. So we'll get an x squared plus 2xh plus h squared minus a 3x minus 3h plus 1 minus x squared plus 3x minus 1. And we can see when we do that, the x squareds cancel out, the 3x's cancel out, and the 1's cancel out. So our limit as x goes to x plus h will look like 2xh plus h squared minus 3h all over h, which again we can see the h's will cancel out of everything. We get a 2x plus h minus 3. Plugging in x for x plus h gives us 2x plus 2h plus h plus 3, which we can rewrite as 2x plus 3h plus 3. There's our instantaneous rate of change at x plus h for this particular function. And again, all this is giving us is a formula. So once we know what our x and our h are, we can find the value of our instantaneous rate of change for any points on the domain of the function.